Have you ever noticed how Greenland looks massive on most world maps? Almost as big as Africa? It's a detail that often goes unquestioned, even though it's right in front of our eyes every time we look at a map in a classroom or a textbook. That's one of the most persistent illusions in cartography, and it's fooled generations of map readers. In reality, Africa is over 14 times larger than Greenland. If you look at a globe, the difference is obvious. Africa dwarfs Greenland by a huge margin. This isn't a careless mistake. It's a side effect of how we flatten our round planet onto a map. Turning a three-dimensional sphere into a two-dimensional rectangle is a tricky business, and something always gets distorted in the process. The culprit is usually the Mercator projection, a map designed centuries ago for navigation at sea, not for showing true land sizes or proportions. As you move toward the poles, the Mercator map stretches land masses dramatically, making places like Greenland look enormous and shrinking equatorial countries so they seem much smaller than they really are. This distortion doesn't just change the way we see geography, it can also influence how we think about the importance and power of different regions. Every flat map of the world distorts something, size, shape, or distance, because it's impossible to represent a sphere perfectly on a rectangle. Each projection makes its own compromises, and no map can show everything accurately. Map makers must choose what to show accurately and what to sacrifice. Their decisions shape the way we understand our planet, whether we realize it or not. Understanding these trade-offs is the first step to reading maps critically. It helps us question what we see, rather than just accepting it as fact. The next time you see a world map, ask yourself, what story is this map telling? And just as importantly, what is it hiding from view? Imagine peeling an orange and trying to lay the peel flat. It wrinkles, tears, and never forms a perfect rectangle. That's the mapmaker's dilemma. The orange peel is a perfect metaphor for the challenge of representing our round planet on a flat surface. No matter how carefully you try, the peel just won't cooperate, and you're left with awkward gaps and overlaps. The Earth is a sphere, but maps are flat. This simple fact creates a world of complications for anyone trying to capture the planet's surface on paper or a screen. Flattening a globe always distorts something. Whether it's the shapes of continents, the sizes of countries, or the distances between places, something has to give. You can preserve shape, size, distance, or direction, but never all at once. Every map projection is a compromise, and each one chooses what to keep accurate and what to let go. It's like trying to wrap a basketball with a sheet of paper. You'll always end up with folds and gaps. The paper simply can't stretch to fit the curves, just as a map can't perfectly fit the globe. Map projections are mathematical strategies to manage these distortions. Cartographers use clever formulas and creative thinking to decide which features to prioritize. Each projection makes trade-offs, prioritizing certain properties for specific uses. Some maps are better for navigation, others for showing true land sizes, and some for visual appeal. There's no single best map, only the best map for a particular purpose. The right map depends on what you need to know or do. A pilot, a demographer, and a student all need different kinds of maps. Each profession relies on maps that highlight the information most important to them. Every map lies in its own way, bending the truth to fit its job. These distortions aren't mistakes, they're necessary choices. The orange peel never lies flat, and neither does the world on a map. Both are reminders that some things just can't be made perfect. The key is knowing which truth your map is bending. Understanding these choices helps you read maps more wisely and use them more effectively. That's the art and the challenge of cartography, balancing accuracy, purpose, and creativity to represent our world as best as possible. To solve the orange peel problem, mapmakers use projections, mathematical recipes for turning the globe into a flat map. Imagine shining a light through a globe onto a surface. The shape of that surface, cylinder, cone, or plane, determines the projection. The three main types are cylindrical, conic, and planar, azimuthal. Each projection distorts the world differently. The goal isn't to eliminate distortion, but to control it for a specific purpose. Some projections preserve shape, conformal, others preserve area, equal area, but none can do both for the whole world. Every map is a compromise, designed to tell a particular geographic story. The cartographer chooses which property matters most: shape, size, distance, or direction. When you look at a map, you're seeing a series of choices, not a perfect replica of reality. The projection is the map's hidden grammar, shaping what you see. Understanding projections helps you decode the map's message. The Mercator projection is legendary for navigation but infamous for distortion. Created in 1569, it let sailors plot straight-line courses across the ocean, a game-changer for navigation. On a Mercator map, straight lines mean constant compass bearings, making sea travel much easier. But to achieve this, the map stretches everything near the poles, making Greenland and Antarctica look enormous. The Mercator preserves local shapes, which helps sailors recognize coastlines, but it wildly distorts area. This gives a skewed sense of the world, exaggerating the size of northern countries. Despite its flaws, the Mercator became the default for web maps in classrooms, often used for the wrong reasons. It's perfect for navigation, but misleading for understanding the true size of countries. The Mercator is a master of direction, but a notorious liar about size. It's a classic example of how the right map for one job can be wrong for another. Enter the Robinson projection, a map designed to look right rather than be mathematically perfect. It was created to strike a balance between accuracy and aesthetics, offering a view of the world that feels familiar and approachable, even if it isn't flawless. Created in 1963, it was meant for textbooks and classrooms, not for navigation or measurement. The goal was to provide students and teachers with a map that looked good on the wall and made the world easy to understand at a glance. The Robinson projection doesn't preserve size or shape exactly, but it minimizes the most jarring distortions. It smooths out the extremes, so no continent or ocean looks wildly out of place, even if the details aren't perfect. Its curved edges and gently bending lines of longitude give a more globe-like feel. The map's soft curves invite viewers to imagine the roundness of the Earth, even on a flat surface. Greenland shrinks, Africa looks more proportional, and the continents appear familiar, if slightly off. The familiar shapes help people recognize the world, while the subtle distortions are less distracting than on other projections. It's a compromise, not perfect at anything, but not terrible at anything either. The Robinson projection finds a middle ground, making it a practical choice for everyday reference. For decades, National Geographic and the CIA used Robinson maps for general reference. These organizations valued its balanced look, which made it ideal for publications and wall displays. It became the standard for showing the world in a balanced, visually appealing way. In classrooms everywhere, students grew up seeing the world through the lens of the Robinson projection. But it's not precise. Navigators and geographers can't use it for exact calculations. If you need to measure distances or plot a course, you'll need a different map. The Robinson is for looking, not measuring. It's a map to admire, to spark curiosity, and to help people see the big picture. Its strength is honesty. It admits its imperfections and aims for visual harmony. The Robinson projection doesn't pretend to be perfect, but it does its best to show the world as a unified whole. It's the map for seeing the world as a whole, not for splitting hairs over details. For classrooms, living rooms, and magazines, the Robinson projection remains a trusted window onto our planet. Planar, or azimuthal, projections offer a unique perspective. Imagine looking straight down at the Earth from above. The azimuthal equidistant projection, often centered on the North Pole, shows true distances and directions from the center point. It's the map on the United Nations flag and is vital for airline routes and radio signals. From the center, distances are accurate, but everything warps as you move outward. Continents near the edge, like Australia or South America, become stretched and distorted. The map can't show the whole globe. Opposite points are infinitely stretched and usually cut off. This projection is perfect for showing connections from a central hub, like polar flight paths, but it's highly specialized, offering a powerful but distorted view. It's a reminder, change your perspective, and the world changes shape. Every map projection is a trade-off. There's no perfect map, only the right map for the job. The Mercator is great for navigation, the Robinson for general reference, and the azimuthal for showing distances from a central point. The key is to ask, what is this map for? Navigators need conformal maps, demographers need equal area maps, classrooms need compromise maps. Using the wrong map can lead to wildly inaccurate conclusions. The choice of projection isn't just about looks, it's about analytical integrity. For general use, compromise projections like Robinson or Winkle Triple offer a balanced view. Always look for clues. Are the lines straight or curved? How big is Antarctica? Is the map a rectangle or rounded? By understanding a map's projection, you can spot its biases and read its story wisely. The best map is the one that tells the truth you need, if you know how to read it.